We're going to be working through these booklets. Shear force and bending moment diagrams is what we're looking for on here. Today I'm going to talk about moments, the moment of a force, and how we calculate that. And then we're going to look at some tutorial questions, and I'll leave you to have a look at those. The tutorial questions also ask us to draw on this a shear force diagram, and that's what we're going to look at next week. So next week we're going to look at shear force diagrams and bending moment diagrams. But today we're going to focus on the basic calculations that you need to do to be able to produce those diagrams, which is finding the moments and what's going on, finding the reaction forces on these beams. So it's all based around a beam. And if we look at this first beam here, we represent it like this, with an arrow pointing upwards to represent the reaction force at one point, and another arrow to show the reaction force at another point. So we would commonly label them A and B, and the calculation that we're going to do is to try and find what force is acting on this beam at these 2 points, A and B, to hold up the beam. What is the reaction force? So if we have a point load, then it looks like this second diagram down here, and then finally a uniformly distributed load, often abbreviated to UDL, uniformly distributed load, which we then represent by this wiggly line along the length of the beam, and so UDL. And if we've got a uniformly distributed load, that means it's all spread evenly across the beam. So what we tend to do is to try and work out what's the reaction of this force downwards, what's the resultant of this downward force, by assuming all the mass is acting in the centre of the UDL, and then that's treated as a point load at that point, a bit like this second diagram here. Okay, so that's the way we draw these things. Let's have a look now at these moments. So moments of force. Moments are taken around a pivot. So let's draw an example. So that might be some sort of lever. This black line here is some sort of lever, and it's pivoted at one end. That's this end here. So this is the pivot. If we have some sort of force acting downwards, then assuming this situation is balanced, there must be an equal and opposite force acting upwards to balance it. And so if I assume there's another force, let's call this the reaction force, acting up there, then there must be a balanced situation there if this thing's not moving. And we're always going to be concerned with structures on this course. What are the stresses on beams and so on in a given structure that's being designed, and the assumption is always made that this structure is balanced, it's not moving, it's rigid, so therefore all the moments and all the forces must be balancing each other. So we're assuming it's going to be a balanced situation. If you think about it, the effect of this force, down force, if we think about levers for a minute, the effect of this force is more than the size of the force. It's also to do with how far away we are from the pivot around which this thing's turning. We've all used levers before, crowbars, so you know that the further you are from the point of action, the pivot in this case, the greater the effect of the force that you're using. So we define this thing called the moment of the force, which is the force multiplied by the distance the force is away from the pivot. So The moment is defined as force times the distance, and that distance is measured from the pivot. So we can define this thing called the moment of the force. The unit is the unit of force, newtons, times by the units of distance, in almost invariably meters. So we would measure moment in Newton meters. We also talk about the direction of these moments. So if we take the pivot and we imagine this thing rotating around the pivot, this lever rotating around the pivot, then it can either rotate clockwise or anti-clockwise. So we define things called the clockwise moments. And the clockwise moments are all the moments where the force is trying to turn the beam clockwise. So if I had this force here, F, that we've talked about already, acting on its own, the beam would be rotating clockwise. So this is a clockwise moment, the moment associated with that force. The reaction force, if it was acting on its own, would be trying to turn the pivot anti-clockwise. So that reaction force is contributing to the anti-clockwise moment. If I had more than one force on here, let's say I had another force acting down there, so force 2, then I would have two forces turning the thing around clockwise, and I'd have to add up the moments of each of those forces. So I'd work out what is this force times that distance, and that would give me that moment, and I'd multiply that force by that distance to get that moment, and then add them together, and that would be the total clockwise contribution. So if the thing is balanced, we say that clockwise moments and hereafter abbreviated by clockwise moments must equal anti-clockwise. I'm going to run out of room. Moments. Hereafter called anti-clockwise moments. So anti-clockwise moments must equal clockwise moments if the thing is balanced, which it's going to be. And in the notes that you've got, that's called Rule 2. For no other reason than that's the second rule that was written down on the worksheet that you've got. Clockwise moments equal anti-clockwise moments. If we look at this situation again, we've also got a situation where if we've got a balanced beam, which this is, so some sort of balanced beam, the total downward force on this beam, however many forces there are, must equal the total upward forces acting on this beam. So there'd be some sort of force there, another force there, there may be something else acting upwards. All the upward forces must balance the downward forces, otherwise the beam would be either moving up or down, wouldn't it? Okay? So that rule can also be applied together with Rule 1, which is that up forces equal down forces. In a balanced situation. We're always referring to a balanced situation. So let's have a look at an example. Let's say we've got a beam, and the length of the beam is 5 meters. And we have one force acting down here of 20 newtons and another force acting here of 10 newtons. And this distance here is from there to there is 1 meter, and from there to there is There's two ways that we can set out the problem, and you'll see both ways used in different situations. So I want to show you both ways. The first one I'm going to show you is probably the way I would do it, because that's the way I'm used to doing it in the past. But then we'll look at the way that may well be done in certain engineering scenarios. So the first thing we do, so this is method one, if you like. So first method. What we do is we add up all the clockwise moments, and then we add up all the anti-clockwise moments, and then we put them equal to each other. So I will label, first of all, I'm going to do the clockwise moments. But the clockwise moments and the anti-clockwise moments that we're going to work out are all about a pivot. So the first thing to do is to decide which end we're going to call the pivot. So what we do is we say, I'm going to call, say, let's label this end A and this end B. So let's say I'm going to call this end A the pivot to start off with. So it's pivoted at A. That means I can then calculate what this reaction force is at B, using the method we just looked at the other screen. Once we've done that, we then switch our idea and make the pivot at point B, and then we can find the reaction force at point A. So what we do is we just assign the pivot to various points on the lever, and then find moments, clockwise and anti-clockwise moments about that point. So method one, clockwise moments about A. So let's subscript A means we're assuming the pivot's at A. So now we take each of these forces that are acting on the beam and ask ourselves, is it going clockwise or anti-clockwise? Well, this first force, the 20 Newton force, is trying to pull it round clockwise. So that's, if it was acting on its own, it would be going clockwise. So this is contributing to the clockwise moments. So that's going to be 20 newtons, which is the force, multiplied by the distance of that force from the pivot. So if this distance here is 1 meter and that's another meter is 2, 5 meters altogether, this distance here must be 3 meters. Okay, so times 3 meters. That's the contribution for the 20 Newton force, if you like, if you want to label that. That's a 20 Newton force. That's 3. Okay. Plus, now we're going to do the contribution for the 10 Newton force. And what's that going to be? 10 multiplied by 4. Right. And there are no other forces pulling the thing around clockwise, so that will be the sum of all the clockwise moments, which equals 60 plus 40, which is 100 Newton meters. And then we find the anti-clockwise moments about A. So anti-clockwise moments about A equal, right, I just look at this one because we'll look at this together. So what's the anti-clockwise moment about A? The only force that's acting anti-clockwise is the reaction force at B. So we'd label that RB for the reaction force at B. So that will be RB times the distance, which is the full length of the beam, 5 meters. So RB times 5, which is 5 RB. And then, being good engineers, we would state the rule that we're then going to apply next. In a balanced situation, clockwise moments, anti-clockwise moments equal clockwise moments. So we'd state that, and we'd say, therefore, RB, 5 RB must equal 100. Okay, so therefore RB equals 100 divided by 5, which is 20. And RB equals 20 newtons. So that's the reaction force at B. So what load is this support B taking? A force of 20 newtons. So I need to make sure that my support can take a load of 20 newtons. Now, I want you to assume the pivot is at B and work out the reaction force at A using exactly the same method. Beware when you do it that you consider clockwise and anti-clockwise moments correctly. This time, if I consider it pivoted at B, then this 10 Newton force is going to try and turn it round anti-clockwise, isn't it? So what I want you to do is a similar method, add up all the clockwise moments and the anti-clockwise moments, and then try and calculate for me the reaction at A. So hopefully you got that the clockwise moments is just the reaction at A times 5 meters, and that the anti-clockwise moments this time will be 10 newtons times 1 meter, which is the distance from this pivot at B, plus 20 newtons times by that distance, which is 2 meters. Okay? And then you get 50 newton meters altogether. So the next step, put them equal to each other. So anti-clockwise moments equals clockwise moments, and therefore 5RA equals 50. So therefore RA equals 10 newtons. And if we go back to our original diagram, we can now write that RA is 10 newtons. Now if you look at this diagram, you can see that the total upward force is 20 plus 10 is 30 newtons, and the total downward force is 20 plus 10 is 30 newtons. Rule 1 is confirmed. Okay, total downward force equals total upward force. You could have argued that once I've got the reaction force at B, which is 20 newtons, why not just subtract that from 30 to get this as 10? Okay. I would say that the danger with that is if you get this wrong, then you're going to get that wrong too, aren't you? And if you're doing a real problem and you want to know this and you haven't got a lecture in front of you to say yes, that's right or wrong, I would actually use rule 1 as a check. So I'd do exactly what you've done, and then I would, now that I've got my two answers and total up equals total down, I can be fairly confident I've done it correctly. So don't automatically just use rule 1 for the other one, because that could be used to check you've not made a mistake. Okay. So that's quite straightforward, isn't it? Okay. There's method 2 that I want to show you. Let's put that underneath. I'm not going to do the whole thing, so this is method 2. It really just comes down to convention. If we look at this beam, we could say that the sum of the moments is 0. So what that's saying is clockwise moments equals anti-clockwise moments. So in very short mathematical statement, we're saying that the sum of the clockwise moments and the sum of the anti-clockwise moments together must equal 0. The sum of the moments must be 0 when it's balanced. So we'd find the sum of the moments about A must be 0. So we would assume the pivot was at A, and we'd say, in that case, we're going to talk about, say, anti-clockwise moments being positive. So we put a little arrow around there saying, right, I'm going to treat all anti-clockwise moments as positive, therefore clockwise moments must be negative. So then I'd go through the same problem. I'd say So therefore, clockwise moments are going to be treated as negative. So I'm going to start off by saying anti-clockwise moments, which is RB, sorry, times, so it's 20 newtons times 5 meters gives you my clockwise moments. So I'm going to say R at B times 5, so 5RB, minus, because now I'm going clockwise, 10 times whatever it was, 10 times 20 times 3 meters, minus 10 times 4 meters equals 0. So I'm doing the same problem, but I'm using a different approach. So then I'd say 5RB minus 60 minus 40 is minus 100 equals 0. And then I've got a little equation to solve, and I'd actually end up adding 100 to both sides to say that 5RB equals 100 and RB is 20 newtons. So in other words, I'll end up with exactly the same answer. I've just used a different approach to the problem by saying that the sum of the moments equals 0. I'm used to using the first method, so I sort of like that one, but I can see how this works, and you might prefer that. Okay? That's quite a nice little way to say it. The sum of the moments about a pivot A is 0, and I'm taking all anticlockwise moments as positive. So that's all written in one very small little statement, and then you can go ahead and do it. That makes sense? Okay. So looking at the tutorial sheet now in this sheet, for each of these examples, for now, don't worry about the shear force diagram, just calculate the reaction forces using moments at each of these supports. What's the reaction force at A? So if we label this A, what's the reaction force at B? So we'll label this B. Okay? You need to take into account what's going on if we've got uniformly distributed load. For goodness sake. Here, then I could just point this out to you. If we look at this example, the uniformly distributed load, 2 kilonewtons per meter. So that means the force that this beam is exerting is a force of 2 kilonewtons for every meter of length. So if I want to find the total resultant of that force, I multiply, so the resultant equals the 2 kilonewtons per meter rather, multiplied by the length of the UDL, which in this case is 8 meters. So I'm going to get 2/8, 16 kilonewtons acting downwards, and this is going to be acting, in this case, in the middle of the beam, because the UDL is across the full length of the beam. So in the middle, I've got a reaction force of 16 kilonewtons. So now I treat the problem as a point load of 16 kilonewtons acting down. Okay? It will have consequences for the shear force diagram, the fact that this is a uniformly distributed load, but we'll worry about that next time. Okay? As far as the reaction forces are concerned, you just treat it like a point source in the center. So if we look at question number 3, anticipating the next question, when you get to that, you'll see that this time you have a UDL that's from the 5 meter mark to the 20 meter mark. So now you've got a point source of 8 kilonewtons acting down, but also a UDL of 2 kilonewtons per meter acting down. So what I would then do is I'd find the resultant and assume that's acting in the middle of the UDL, which is from there to there. Okay? So 2 kilonewtons again multiplied by the distance will give you the size of that force. Right? I'm going to give you a block of time now to work through them. There's quite a few. Look, 4, 5, 6. There's another sheet. with combinations of point forces and UDLs. Work out the reaction force at every stage. When you get to the next page, we'll look at these, but think about what effect this has. Look, the fact that the beam is pivoted not at the end but here, what effect will this have when I take the pivot? Just think about clockwise and anti-clockwise. If this was acting on its own, would it be acting clockwise or anti-clockwise around that pivot? Or that pivot, whichever one you take. Okay? Right, I'll pause this there and let you have a go.